Hello, my name is Anabela Aguilar Ramirez, and in this video, I will be presenting my database project titled Investment Portfolio Tracking Database, which was implemented using Microsoft SQL. So the purpose of this database is to track investors, their portfolios, financial assets, brokerage platforms, and the trades executed within those portfolios. This system allows analysts to review trading activity, portfolio performance, and investment exposure using structured relational data. I'm doing this project for my database systems. All right, so in here we can see the year diagram that I created for my portfolio tracking subsystem. I use lossy charts. So in here we can see basically these database models a simplified investment tracking system using a fictional firm called AAR, which basically is my name. So yeah, the system tracks investors who own portfolios, and each portfolio contains trades that involve different financial assets, so such as stocks, ETFs, cryptocurrencies. So the trades are executed through brokerage platforms, which are also tracked in this database. The design follows relational database principles, and it ensures that each entity that we can see, we have different tables of the entities, is stored in its own table to reduce redundancy and maintain data integrity. So here we can see the investors table, which stores information about the individuals who own investment portfolios. And our primary key is investor, which uniquely identifies each investor. So it assigns an ID to each investor in our database. Other attributes include the investor name and the risk profile, meaning if they're conservative, moderate, or aggressive in their investments. Then we have the portfolios table, which stores each investment portfolio, and each portfolio belongs to an investor. So, and it's represented using the investor ID foreign key to connect to our investors table. And this one creates one-to-many relationships where one investor can have multiple portfolios. Then in our assets table, this table stores financial instruments like such as the stocks, ETFs, or cryptocurrencies, and each asset has a symbol, asset type, and sector classification. I'm keeping the assets in a separate table to avoid repeating asset information in every trade. Then we have the brokers table, and then this table stores brokerage firms or trading platforms that are used to execute the trades. And this allows the system to analyze trading activity by broker. And then we have the trades table, which is our main transactional table in the database, and it records every trade made within a portfolio. Each trade references a portfolio, asset, and broker through foreign keys. And the additional attributes that we have include trade date, the trade type, quantity, the trade type, meaning if they're buying or selling, then quantity, and the price. So to explain the relationships of the table, I think it'll be easier if I show you the part 3 of my project. So in here we can see the logical design of my ER diagram in more detail. So we have the tables, as I mentioned before, investor tables. There's the people, basically, or clients who can own one or more investment portfolios. So this helps us to know which portfolio belongs to who. And so we have our investor ID, the investor name, and then the risk profile, as I mentioned. Then we have the other table, which is portfolios, that stores each investment portfolio owned by an investor. So one investor can have multiple portfolios for different goals, like long-term growth or dividends, depending on each client's case. For this one, we have portfolio ID, investor ID, portfolio name. And then we have our table for assets, and it stores the financial instruments that can be traded, like the stocks, ETFs, and crypto. In here we have the asset ID, asset symbol. Also for asset type, we have different categories, as I mentioned before, stock, ETF, crypto, or bond. And then the sector, meaning if I'm getting maybe some stocks for Apple, that'll go to technology. And then for the table 4, we have the brokers table, which are the brokerage firms or trading platforms that are used to place the trades. For example, there is one that is called GBM, so that'll be one. So we have the broker ID, the broker name, and then the platform, which is, for example, web or mobile. If you're doing it through the website, then it'll go through the web. If you're doing it from an app, it'll be a mobile. Then we have the trades. In the trades table, we record every buy or sell, every transaction placed in a specific portfolio. Basically, this is our main transactional table in the database, and it stores different information such as the date, type, quantity, price, etc. So we have the trade ID to identify each unique transaction. Then we have the portfolio ID, asset ID, brokerage ID. So basically, this table is connecting to pretty much all the other tables. So this is our main one. Then the trade date to know when the trade happened, and the trade type, which was buy or sell, and the quantity, the number of units or shares that are traded, and the price per unit for each trade. Then, well, as we saw in the diagram, we have the different primary foreign key and foreign keys. For this design, I didn't use any composite key. And then, well, for data types, to create the database in SQL, it was very important to identify which attribute was. So as we can see, for investors, we have investor ID, and we categorize it like integer. We have investor name. We selected bar chart, not null, since the names can vary in length. So 120 was a good limit for any fictional names that we wanted. Then for risk profile, we selected varchar since it's like a small text. And we only have three different options: conservative, moderate, and aggressive. Then for the portfolio ID, we select their integer identity. So for investors ID, integer, and then we selected not null because every portfolio must have an owner. So it's impossible to have a portfolio ID, a portfolio basically, without the investor. The portfolio name, varchar, same thing because we wanted a decent amount of characters for the name since it can vary. And then strategy, we selected varchar, and for assets ID, integer identity. Then for asset symbol, varchar, and especially since most of the tickers are very short, so it's usually like maybe 4 characters or so. So 15 seemed like a decent number. Then for asset type, we selected varchar, since this is basically storing the category level, like if it's a stock, ETF, cryptocurrency, etc. For sector, we selected 60. And for this one, actually, we allowed to be null because maybe the sector can be missing for some certain asset types, and that gives us that flexibility. Then for broker ID, we selected integer in identity. Then for broker name, we selected varchar, and platform, again, varchar, since it's just very small amount of characters, like web, mobile, desktop, etc. For the trades, the trade ID, we selected integer identity, portfolio ID, integer, no, same for asset ID, broker ID, same. All of these have been mentioned before in the other tables. And then the trade date, the date is needed for each transaction. So this was assigned as not null. Then for trade type, we just did varchar of 10 since it's only buy or sell. Then for quantity, decimal. So this is the first fraction of quantities, which are very important for the crypto, and some large quantities if needed based on whatever transaction we're making. Then for the price, I selected decimal because it's money related, so we needed that. And then for the relation description, so for this database, the investor can own multiple portfolios, but each portfolio belongs exactly to one investor. Each portfolio can have many trades because trades happen over time, and each trade is tied to one exact portfolio. For the trades table, this connects trading activity to reference data, and like each trade involves one asset, which means that one asset can appear in many trades across different portfolios. And each trade also uses one broker, which means that a broker can be linked to many trades. So these are one-to-many relationships, and it makes it easy to analyze trading history and summarizing the activity by the investor, asset type, portfolio sector, etc., or broker, while keeping the design normalized and avoiding data duplication. After creating the schema, I inserted fictional sample data into each table. I use SQL. In here, we can see that I created the database. It's called investment tracker. And then here we can see the different tables that I've created, which are my assets table, brokers table, investors table, portfolios table, and trades table. So in here, I've used the select statement to show all the fictional data that I added to all of these tables. So I execute it, and then in here we can see the results and the data that was added. For example, we can see the investors and then their portfolios, like investor, the portfolio, and then the trades that have been executed for. So basically for, let's say, investor one, which is me, we have my portfolio. We have two different portfolios. One is named Core Growth, the other one Dividend Focus. And then for the asset ID, different assets, and then the different brokers that exist. And here is the transactions. So trade one, asset one. So basically, for my portfolio number one, I bought the Apple stock using the Norbridge brokerage. So now we're gonna demonstrate that the database actually works. We created different queries. For our first query, we are demonstrating a join across multiple tables. In this query, it joins the trades table with the portfolios, investors, assets, and brokers table. So the join condition connects the foreign key in the trade table, the primary key in the related trade tables. For example, the portfolio ID connects trades to portfolios, investor ID connects portfolios to investors, then the asset ID connects the trades to assets, and broker ID connects trades to brokers. In here we can see the results, which are the investor name, portfolio name, asset symbol, broker's name, trade type, quantity, price, and trade date, and the results are sorted by trade date in descending order, so we can see the most recent trades appearing first. Then for our second query, we demonstrate an aggregate function combined with a group by clause. So in this query, the count function calculates the number of trades associated with each investor. The query joins the investors table to the portfolios table and then connects portfolios to the trades table. And we use the group by clause to show the results by investor name. So each investor only appears once. And then we use the count function to count how many trades belong to each investor. So for example, Annabelle has 5 total trades. And then the results are sorted in descending order. So the investor with the highest number of trades appears in first, and so on. Query number 3, we are showing the filtering and sorting data. So we're using the where and the order by clause. So where filters the trades data, the trades table, so that it only shows the rows where only the trade type is by. And then for the order by class, it sorts the result by trade date in descending order in here. For query number 4, we are calculating the net investment amount of each portfolio. We're using the query joins. So we're using the portfolio table with the trades table using the portfolio ID field here. And then we use a case statement to treat buy transactions as positive values and sell transactions as negative values. So the trade value is calculated by multiplying the quantity price, and the sum function then adds these values together for each portfolio. So then the group by clause groups the results by portfolio name, and then these there is a group by. It's ordered by the net investment amount, so like the total amount in descendant order. So the ones that are having a higher net investment amount shows first, and so on. So then for query number 5, we are doing a trading activity by asset type. So our different asset types, crypto, stock, ETF. Basically, it takes the asset table with the trades table using the asset ID. And then we use the group by clause to group the results by the asset type that I mentioned before, stock, ETF, cryptocurrency. And then the count function, it calculates the numbers of trades for each asset category. And then the sum function calculates the total trade value by multiplying quantity by price for each transaction. And in here, we can see the total trade value in descendant order. Lastly, we are doing the trades we're doing a query that analyzes trades executed to a specific broker. In this case, we're looking at the Norbridge brokerage. So for this query, it joins the trades table with the brokers table and the assets table. So we're using the where clause to filter the results so that there is only the trades that were executed by this broker, the Norbridge brokerage. And then our output displays the broker's name, asset symbol, trade type, quantity price, and trade date. And this is showing by trade date in a descendant order. These are pretty much all the tests that I did. It shows how the relational database can be used to analyze investment activity, summarizing trading behavior, and combining data across multiple relational tables while using SQL. I learned a lot in this class, and it was very fun to create this project, but this can be used in a real case scenario for a real company. So thank you so much for watching, and see you soon.